Miren and I wanted to learn about how to measure U-value or thermal transmittance, and for this we are meeting with Stefano Avesani at the EURAC Research Laboratories.
Good. We are here for showing you the U-value machine, U-value measurement machine.
Let's explain, Alessandra, what we can measure here.
Yes, with pleasure. So with the machine, we can measure the thermal transmittance. So we need to have one facade sample, and we insert this in this fixed part. Okay, the facade sample will be surrounded by something which is very, very insulated. So all what is white part means no heat flux. Okay, while our facade sample stay in the middle.
So that is the facade sample of this test.
This is the facade sample, as you see, is an homogeneous. Is made of different materials, so it's inhomogeneous. We need then this indicator, the thermal transmittance, and we can measure it by applying a temperature difference.
All right.
Okay, so that's why you see two blue boxes here. On the left side here, you see the so-called hot chamber. Okay, so here basically we apply some temperatures which may be from 16 to 30 degrees normally. Okay. And in this way, we produce there the heat, and then we want the heat to pass through the facade sample that we have seen before, and it goes then into the cold chamber. Why this is cold chamber? Because it can go below 20 degrees, below zero, and in this way we have the temperature difference. The thermal transmittance is exactly how much heat we get by a temperature difference per square meter, okay? So basically we force the heat to enter here. Once the temperature here is set, we set the temperature there, and then we measure how much heat is passing by our facade sample, okay? Of course, this is very important. Measuring the heat we input here, that is electricity finally.
And I guess I see a gap between the heat source and
Exactly.
the actual chamber. I guess it's because it's important to minimize any loss, right?
Exactly, we have to minimize the loss. So all what is in the smaller chamber is our heat flow input. And we don't want the heat to go around, only through the facade sample. And this way we can measure it quite precisely, accurately. Yes, exactly.
And it's usually the same temperature difference in the test, so it depends.
So if we want to get the thermal transmittance, we set quite standardized difference of temperature levels. But then we might use the same machine to also characterize the thermal behavior at defined temperatures. So we can push again up to 20, down to 20 degrees below zero, or here up to 30 degrees. But in real environment, of course, the temperatures are totally variable, and we can here try to represent, let's say, similar values, but not the same.
And is it important, the temperature that we put in this chamber and in this chamber?
So for the thermal transmittance itself, it doesn't matter so much. It's just a matter of how quick then is the test, let's say. Because the thermal transmittance is just per unit of difference of temperature.
Right.
Yeah.
So we just need to ensure a temperature difference.
Yes, that's the basic of the measurement.
And what are you measuring on the panel actually?
Yeah. So we can then, of course, have some checkpoints here. These are sensors for temperatures at surface.
Okay.
And this allows us to then also characterize the different behavior of the layers of our facade sample, because we said this is not made by only one material, but there are many interactions of heat transfer within all the materials composing the sample. In this case, there is the glass, there is an integrated blinds, and so on. The frame. So many different materials means many different ways of transferring the heat.
And when you can, depending on the prototype, do you also put surface temperature then across the layers?
Exactly. That's very useful because you can then check if something which is very complex behave as you expected in all the layers. Of course, you mentioned something important. This is a sample which costs a lot of money. So this is a testing for something which is advanced, complex. If you have a very standardized facade sample, either opaque as brick walls and or transparent as a window, you can also calculate the heat transfer, which is today quite accurate calculation methods, quite standardized. So you come to the testing, to the lab, when the facade sample is really complex, let's say.
So the U value that you explained to us now, it's an ideal parameter, right?
Yes, exactly. With the U value, we have a steady state, stationary condition. Fixed temperatures, cold, fixed temperature, hot, and then we measure the heat flux once everything is stable. But in reality, the indoor temperatures and then the outdoor temperatures changes a lot continuously, sub-hourly. So we need this is one of the indicators actually that we need to characterize it. The other one is the thermal inertia that we need again a bit idealizing what is then the real behavior. And to do so, we can somehow think to the time that our facade sample need to get to the, let's say, theoretical configuration. So we put 0 gradi in the cold, 0 degrees Celsius in the cold chamber, 20 degrees Celsius in the hot chamber. How long does it take the facade to go exactly at the theoretical profiles of temperatures? That's, let's say, in a way, the thermal inertia. And let's say the higher is this time, the more time we will need to wait until the building somehow getting temperatures. But that's, again, ideal. So in the reality, these two factors, U value and thermal inertia, are those defining sub-hourly the way the buildings lose or gain heat by, let's say, conduction, transmission into the walls.
Or windows, right?
Or windows.
Okay.
You're right. Or windows. Transparent or opaque is the same concept. The most important things I have to add is, in this condition, we don't consider the sun. Okay,
Right.
So it's only driven by temperature difference.
If you were to do the measurement outdoor in a real building, do you then do the measurement at night?
Exactly. We have to wait once the solar radiation effect on the wall are not relevant, and at that point we could even there measure on site the thermal transmittance. Yes, you're right.
Wow, nice.
And then one also relevant thing is that in the facade sample there are different layers, right? So every layer will have a final temperature distribution which is peculiar of that facade sample.
Right.
That's, let's say, occurring, of course, in steady state condition very clearly, because then we will have only one trend inside the layers of the facade samples. But in real condition, this changes a lot, sub-hourly. So that's much more complex to be evaluated.
So all this was about how we measure facades, but we only measure facades when it's something new, unknown, complex, because of course performing tests is something expensive, right?
Yes.
So maybe now we can meet another colleague that is expert of calculation, so we don't always need to perform this complex tests.
Super, let's go.
Let's go to meet her.